whereas I feel like when I'm programming on C#. SharePoint. So
I mean, you're missing a E on power.
well, maybe.
I definitely need to start. Oh.
I just pushed it. It's not closed, so yeah.
Yeah.
Alright, well, I guess we'll just go ahead and get started and take kind of a leisurely pace today. So, I'm Jack Pappas. I'm the co-founder and CEO of a company called Tide Power. And we make a product called GPU.net, which I'll talk about in a little bit. And generally, this talk will be sort of not just about GPU computing and F#, but also about all kinds of little tweaks and optimizations and things that we figured out while building GPU.net. So high performance F# and .NET and GPU. All right, so just a quick background about myself. I haven't met everyone here, so my background is actually in numerical analysis and optimization. I'm not a computer science guy. It's sort of been something I've learned on the fly. I started out doing C# code a long time ago, reasonably, for about 6 years. We built the first, even the first release version, and then some minor versions in C# of GPU.net. And at some point, it just, I'm the only coder at Tide Power. So it's just too much right now. And so I wrote the entire app in C#, and it got to be to the point where it was just unmaintainable by myself. Nothing against C# or anything like that. The code base got so big I couldn't handle it on my own anymore. And so we made a decision, which has been probably the best decision we've made with our company, to go ahead and switch our code base over to F#. So I went back, I took about, I guess it was maybe 3 weeks or so, and I rewrote the entire code base in F#. Some of it is fairly straightforward because it's still going to be, the string builder is going to be the same in F# and C#, right? So we went back into that. We reduced our code base from about we reduced our code base from about 30,000 lines of code-ish to maybe about 6,000 lines of F#. Got a nice speed gain right off the bat, and we've continued to optimize as we've gone along. So, what exactly is GPU.net? So, what we've done is built essentially an implementation of the .NET CLR, just like the .NET Framework or Mono or something, right? We've gone back and we implemented .NET CLR in F#, right? And it's something that I thought originally we could get away with, I don't want to say cheating, but we could have done, part of the work of a full-on compiler, and we could have gotten GPU speed up, and it didn't turn out that way. So, now, to get all the features that we wanted to get, it turned out to be that we essentially re-implemented .NET CLR. Like I said, it's written almost entirely in F# now. I mean, the only thing that we don't use F# for are some example projects. I think our unit tests are still in C#. So, just a brief overview of what we'll go over today. And like I said, we can kind of take a leisurely pace. I was telling Rick just when I walked in that we had talked on the phone, I guess about a month ago, about what we wanted to present in this talk. There's been some really big interest in doing HPC computing and parallel type stuff in GPU with F-sharp. And as I was, writing everything out and building up our presentation today, it just started ballooning out and turned into a ton of slides. So some of it I'll go over, some of it I might just skip over, just briefly mention. I'll post all the slides up later if you guys want to go back and see anything special. Or like I said, just we've got a bunch of time, so feel free to stop me and I can answer any questions. So I'll go over just a few brief performance guidelines and what I like to call the 80-20 optimizations. I'm sure a lot of people have heard of that rule, that what will get you 80% of the performance gain that you're going to get from just doing a little bit of work. And data structures are really, really important in functional code, as I'm sure most of you know. But there are little tips and tricks that you can use to speed up little specific bits of code. So scalability is really, really important in what we do. And that's basically what GPU computing is about, is scalability. How can you take a small bit of code and scale it across 100 or 1,000 cores in a GPU? And F-sharp is really, really good for that in particular, and I'll talk about some of the reasons why. And then I'll talk about specifically parallel computing with F-sharp. I don't think I put it in there, but I'll get into it. There are some things about task parallel library I'll mention in .NET 4, as well as I'll give a little background about HPC and GPU computing. There's, I don't know what everyone's background is here, but if you're just let's say an average F-sharp coder, I don't know that everyone's got into GPU and OpenCL and CUDA and MPI and cluster stuff. So I'll talk about that and sort of how that's accessible and actually really nice to use from F-sharp. And I guess finally I'll touch on supercomputing, if you will, with functional languages and why is F-sharp a really good choice for doing this stuff. Functional languages have some unique features, and F-sharp in particular, that make it really, really nice for these applications. Okay, so the 80-20 rule. Profiling applications is really, really important. You can build a whole application, and it's nice to use the F-sharp interactive and say, hey, I knocked up this whole application with some pipelining stuff and everything else. It's thrown together. It works really great. F-sharp's great for rapid prototyping, right? But even as good as it is for that, there are going to be cases where you mess something up or whatever, and or just mistakenly put a certain function call or something in, and it just kills the performance of your application. I guess one example that I put it in here because I wanted to make sure that I mentioned it. We had built GP.NET, that I ported it to F-sharp. We actually had a shipping version of F-sharp. Everything was going great. I was really happy with the performance of our shipping version. It was getting faster and faster every time we made little changes here and there. And one night I decided, just for the heck of it, I was like, well, what? I think I could probably get some, squeeze maybe another millisecond or something out of this, our execution pipeline, where we go from taking whatever code you want to run on the GPU, we parse it, analyze it, all the compiler type stuff, do JIT compilation. That whole pipeline, I figured, hey, we can squeeze a little bit more performance out of this. And I ran it through the profiler, and as it turned out, I had made a little mistake with one dictionary in our code, where it was actually the code cache, right? Where it's it's JIT the code, and we're not going to read JIT the code every time. We want it just once. I think that in an older version, I had used some kind of whatever data structure. I changed the key, right? So I changed the key to I was using for the dictionary. And I think in the original one, I had just had some kind of basic little record. So I used physical hash, right, that we know from F#. And then at some later point, without thinking about it, with type for inference and all that, you don't have to change it, right? That's the big point of doing that. And I changed the key in it, and I ended up using some big recursive structure. And so it turned out between optimizing that key in the dictionary, and then also if you use the .NET printf stuff, it's actually really slow, right? So I don't know if you guys use that a lot. It's great for like if you need to print something out to the console for the user. But if you try to use it in anything really high performance, where you want to be using like Spring Builder, let's say, right? I was building up the code using .NET. There's a printf, I think it's what printf, something like that, to write formatted strings into Spring Builder, and changing the dictionary key and changing those over to an actual call to string format or whatever increased our execution speed in about 80%. It just locked off a huge chunk of it, and it took me about an hour. And that was already, with a version that we had, our customers were pretty happy with the performance it was getting and everything. And so, that's just an example of we have this code base that is going really well, and you just make a little mistake and it just ruins your performance. So, even if you think it's really fast, if performance is critical for whatever you're building, then profile it just once in a while and make sure that you haven't missed anything. So along the same line, I don't know how many of you have dug into the. Sorry.
Which application did you use for profiling?
I used ANTS Profiler from Redgate. So disclaimer, Redgate has invested in our company, but I bought ANTS Profiler before they did that. So that's sort of Redgate. That makes .NET Reflector and SQL prompt and all that stuff, right? So let's see. Right. So one of the things I don't know how deep everyone's dug into F#. The internals for libraries and then where you looked at it and studied it to see where things were going. But there are some really specific cases that a very small change in your code can lead to a huge change in performance. And I'm talking something like an array, specifically an array comprehension or something that moves over an array from 0 to however many elements in the array, right? So that's actually can get optimized by the F# compiler, but if you start at element 1, it's not optimized, right?
Does Microsoft have a list of the things that are gotcha type of stuff, going from one to the next? I have
not that I know of.
When 2010 came out, there was a transfer from 2005 to 2008, from 2008 to 2010.
Right.
And a couple little, hints and whatever. They still don't have anything to tell you. Don't use this.
Yeah.
Yes, use that.
I mean, that's one of the things. I mean, I've seen some specific guidelines. So one of the things, if you do a lot of low-level interop stuff with drivers and things like that, so we're not based on any other compiler. We don't, emit C or something in the back end and then use some other third-party compiler to build our stuff. Right? I mean, we're full on JIT compiler, so everything we do is down at driver level as far as IPUs and things like that go. And one of the things that changed with .NET 4 that wasn't really announced, and if you switched any applications over that use .NET 4, there's a feature called MDAs, right? It's Managed Debugger Assistance, and they essentially help you find bugs in your app, right? And there's one that's been around since .NET 2, but it was never on by default, and it's on by default, in .NET 4, and that's to detect issues with your p-invoke signatures. And there's tons of these applications out now that they had some kind of fault, slightly faulty p-invoke signature ran fine on .NET 2 and .NET 3.5, and it's the same gen and all that. And .NET 4 came out, and the application just broke. And you track it down. Why is it broken? Well, hey, it's broken, been broken for a while, right? But no one realized because it's such a small bug that no one ever noticed. So there's things like that it's just. I wish there was a list, but I really haven't seen anything super specific. And as far as this goes, with F-sharp stuff, I mean, F-sharp compiler is pretty smart about optimizing stuff, but it's not perfect. So there are going to be little things here and there. I mean, I found the best way for us is to actually just go through, the F-sharp source. If there's something that I know needs to be super, super, fast, one specific little loop or something, and make sure that that's going to be optimized the correct way. And another really, really important thing, a tool that you should absolutely have and know how to use is .NET Reflector. So I think you can also use ILDASM, which comes with Visual Studio, but it's not really, I don't think they've updated in 10 years. So, but .NET Reflector is really good. You should learn, IL if you can. The .NET spec is free and it's a good reference. So if you even learn it a little bit, you can go in with .NET Reflector and see where there may be issues, where something's been compiled, and you can look at it and say, hey, this has gone wrong somehow, right? I was looking at something the other day and noticed that I'd written something a little bit that wasn't written well, let's say. And I put it through, .NET Reflector, and you can look at it and say, okay, well, the F-sharp compiler couldn't turn this into tail call, right? So that's really big. You may never notice it, but the reason that tail call stuff is big is because you avoid overflowing the stack, right? But not only that is that the JIT compiler can turn that into a really simple while loop because it doesn't transfer stack between each method call, right? So it does help performance as well. So it's pretty important. And when you get to stuff like what we do, where if I'm running timing, profiling type stuff on GP.net, I mean, we're talking like milliseconds or microseconds. That everything's got to be super fast. So, like I said, the best way really is to either look at it in IL, profile it, or go through the F-sharp source and something really specific. And also knowing the better that you know IL, it'll help you sort of understand where the F-sharp compiler can optimize it, right? So you can say, well, this can be optimized because this one .NET instruction, this IL instruction checks against 0 versus having to do a binary comparison, right? So a binary comparison, let's say, is some x and y equal integers. Well, it's going to have to do x minus y and then test the result for 0, where if it's just checking something for 0, it's one less operation, right, that the CPU's got to do. So let's move on to data structures. So super important, back to making sure that what you've written is actually the right thing. There's been plenty of cases where, again, I've knocked something out really, quickly. I can't look at the pipeline and stuff together, and bam, it works, and I've done it in 30 seconds, right? Run it, I'm happy with it, but then later on come back to it and say, well, this is not really running as fast as I'd like it to be. Why is that? And so there are specific cases where it's easy to use a certain data structure because it will help get it done quickly, but it's going to ruin your performance or ruin in relative terms. It could be a lot slower by a couple of times, let's say, versus some faster way. So the big one is seek, right? So if you use sequence, remember that's going to use an enumerator under the hood. So every time you're going to go to the next element, it's making a method call, it's got to update state and all this stuff, right? Whereas, let's say with an array, you're getting a chunk of elements that just, okay, go to the next array, and it just updates the array index and under the hood in the CPU, it's just updating memory drift, right? And I can just walk all that at once. And so you don't really.
I was going to ask about the lazy with F-sharp list. The lazy itself has to do an invoke and then check and see if something is cached.
Right. But I think under the hood, the lazy, if you force the lazy, then it does kind of optimize, monitor some pulse, whatever they've done to make it really crazy, ridiculous. And it's not going to be. If you think about it, if you have a seek, let's say, of 1,000 elements, right, and you have a lazy with a list, well, if you want to get the elements in the list, you'll need to force the lazy once, right? So it's only going to do one sort of monitor, pulse, check, whatever it is. Whereas a seek might have to do, it's going to do that on every element, so you're going to get it 1,000 times, whatever, right? So, I mean, again, it's just one of those things that, like, we're talking really, I need to get ridiculous maximum performance out of applications. This is the kind of stuff that needs to be taken into consideration, right? And so, like Rick said, in some cases, what you could do if you don't really need lazy evaluation per element, wrap your computation in a lazy and then use a list or an array or something like that. You only have to do it once; it'll be cached, right? And then you can just force it. You don't have all this overhead every single time you need to traverse the list or whatever.
I came a little late, I'm sorry. Does any of these things apply to C#, or it's all only for?
I mean, they can. I mean, I know now in .NET 4, it's got lazy class, so F#, can compile stuff back to .NET 2, right? And it will inject its own versions of like a lazy, right? They have their own implementation of lazy for .NET 2 in F#. But if you compile for .NET 4, it'll use the built-in base class library, lazy class, right? So that
Using C# when you test.
no. So what I'm saying is that in C#, if you wanted to, that would be you could use the lazy class and do the same kind of optimization, right? Instead of using an enumerable, you would just build up some array or use a list, right, a generic list, and then you only compute it when you need it to with compute it inside a lazy, so it's only computed once, right? That if you have some function that generates the list or something, it's only you only call that function once and then it's cached, so that all of you. So all right, so another one. So seek and list, right? So if you're computing all the elements of something at once, right? You've got a function that's just going to return a bunch of stuff, and then that's it. You're not going to actually be tacking elements on later or whatever. Then just use an array, because if you're going to have all the stuff at once anyway, then what happens is if you're traversing a list, right? It's a linked list under the hood of an F#. And so what's going to happen is every time you need to traverse that element, it's going to have to be another memory fetch, right? And it could be, that element could be anywhere, right? I mean, they don't have to be consecutive in memory. That's the idea of using a linked list versus array. So it could be that if you're traversing a huge list, then it's just constantly just ruining your CPU cache, and invalidate it, make another fetch, check the next pointer, invalidate the cache line, make another fetch from memory. If you use an array, right, well, it can just fetch a whole block from memory and store the CPU cache, traverse it, it's much faster. And again, this is something that you may not notice if you have 5 elements or something, right? Or in fact, you won't notice it. But if you're doing 1 million elements or 100 million elements or something like that, it's definitely noticeable in a big way. So, and I'll actually talk about that kind of stuff in a little bit. And again, another thing, for small numbers of elements, use just use an array to, like I said, to avoid the extra memory fetches. But you can also use like a resize array, right? And build it, and then when you're done, if you need to build a list, build it with a resize array, then convert it to array and return, right? So you're not trying to append lists or arrays. Because if you remember in F#, right? So things like the range operator and all that. Arrays in F# are a little bit funny because they're mutable, but they're kind of treated sometimes like they're immutable. And so if you have something like the range operator, right, it will actually copy the whole array, whatever range you've chosen, and then copy that into a new array and return that. And so if you're using, let's say, the range operator inside a recursive function or whatever, then it's going to be copying stuff into an array. Then put that to the next iteration, copy similar stuff into a new array, and so forth. So you're really creating tons of these array copies over and over and over for no reason, right? So the best thing really would be just use an array and kind of keep track of the range yourself, or better yet, use there's sort of a little known class or structure, I think it is, inside the base class library. It's been around for forever. It's array segment. I think it's system.array segment, right? You use that. It's really just a wrapper for an array, and then it says, here's the start, here's the end. And the nice thing about that is that you can kind of keep track. It's almost like a fake range operator, right? So you're really just passing the array segment around, but you're not copying stuff over and over and over. You're just modifying what's the start and end index. So it's much faster than repeatedly making these copies and stuff. And this is actually a really big one that I didn't find until later. So when I ported all our stuff over from C# to F#, I was like, yeah, immutability, everything's got to be immutable, and I've got to do everything functionally. And so I see the map, right, the immutable map in F#. And the problem with that, though, is that if you're just going to build a map up and then use that as some kind of like a lookup table, and it's never going to be something that you're actually passing around, adding stuff, subtracting stuff, and really it's immutable, so you're not modifying it, but see what I mean? Like you're just using it to create other instances. If you're just going to build it up once and then read from it, then you should use the dict operator instead, right? So that's built into F#. It takes a sequence of tuples, okay? Your key is a key and value tuple, kind of like key value pair, but not. And if you do that, what it does is it just creates a dictionary under the hood and then wraps it in an immutable wrapper so that it can't be updated by accident, right? So the important part there is that if you have a lot of elements in the map or the dictionary, it's really noticeable after 1,000-ish elements. So a map lookup is O log n. So I've got something here that's a little bit for set actually. It's fine up to a certain small number of elements, and you'll never notice the difference really. But as it grows bigger and bigger and bigger, you can see a big performance gain there. And if you're if it's not something that you really need to have the map where you can merge them together and do all this stuff, then just use a dictionary. It's faster and it's pretty simple. So right, and so just a quick tip with that: if you build your dictionary, if you use the dict operator, and you build it, just pipeline into it, right, using an array or a list, right? They implement the IEnumerable, which is what their sequence in F#, which is what the dict operator takes, and it's going to have to do a count to get to determine the size of the underlying dictionary that it uses. So if you use an array or a list, that count is available right away, right? So if you use a sequence, it's got to compute the sequence, then just to get the count, right? And then it'll create the dictionary. Then it's got to traverse the sequence again to build the dictionary, or it'll have to copy it into some extra thing, some temporary behind the scenes variable. So if you build it from an array or list, that counts available right away. It just checks it, and then it will traverse the array or list once to build the dictionary. All right. So before we jump into the next part, I want to show just a quick F#. I just want to show a quick demo of what exactly I'm talking about here with using the right data structure. So we'll create a random set of integers. So I've created this little function here that just uses a system.random, just dumps integers into a set until it gets to a predefined size, whatever we want, right? So we'll say so another thing with set, by the way, I guess while this is building, just like map, it uses a similar data structure under the hood. So if you use a set, it's log n insert. So if you have something like this that's just going to take a huge number of elements and throw them in the set, then you're basically getting like n log n, right? So it's going to be kind of slow after a bit. So another little trick that you can do if you target .NET 2 or 3.5, right, is to use dictionary, basically as a cheap hash set, which is available in .NET 4. So I think that's what set in F# we use. If you target .NET 4, we use hash set, which has 01 insert and all that stuff. But if you're targeting one of the older ones, then maybe use a dictionary if you need super fast performance, or you're just inserting a bunch of elements. Look up later. All right, so we create that random set. So now, so let me describe what I'm talking about with. All right, so I guess everyone see that all right? So here's a really simple function, right? Which all it does is it takes a set called mySet, which we'll throw that random set we created into it, and it takes a filter function, which is predicate, right? It takes an element, returns bool, and a mapping, which returns an element, takes an element of like t and returns t as well, right? So we're going to take the set, we'll filter it using the filter, right? So we're traversing the set and applying this filter, right? So it's going to traverse every element of the set, apply the filter, and it will create another set, right, with whatever elements are left over. Then we'll turn the set to a list, and then we'll do list.map, and we'll map each of the elements that was from the set, which is now a list, into a new list, right? And then we'll turn the list into an array, right? So if we time that, I'll time it in a second, but here's an optimized version, right? So what you could do instead is, because you're really just traversing this thing, this set, right? You're going to map, you're going to filter out the elements, and then you're just going to convert it into using the map, and then you're going to turn it into an array. Well, if you just build it all here using a fold over the set, right? And then use a resize array, which is a list, generic list, right, in C#. And especially important, you initialize it to a good size where it won't really have to be resized under the hood. So list is really just an array, right? And it keeps track of how many elements are in the array or a list. And then, as it has the elements that needs to resize the list to add more capacity, it will just allocate a new array, copy the original elements in, and then we'll have that, use that. You'll copy the stuff in. So if you initialize your collection here to a size where it won't have to be resized ever, or maybe it'll have to be resized once in some cases or something, right? Then really, you could even just use a regular array there, but it's just simpler to use a resize array to keep track of things. So you use this list or resize array here, initialize it to the right side, fold over the set, and then for each element, you're really just going to do this thing as pipeline, but you're just going to do it inside this fold here, right? And then you use the toArray function to return. And so you can see, even for a reasonably just defined two basic little functions that serve as the filter and mapping, and I kept them simple because I want everyone to be able to see that even for a really simple function, filter and mapping function, the performance difference is big. Alright, so the filter is just, is it an even number, right? So takes x, x mod 2, 0. And then mapping, if the number is greater than a million, then it returns a negative, otherwise it returns that number. So really simple functions. And if we run the thing there, so, I mean, it didn't really take that long, right, to run this unoptimized one. If we run it a couple times, you can see that, there are a number of, early on GC collections that it has to do, right, because of intermediate data structures that are created. And not really that long, it's 0.1 seconds or 0.12 seconds or something, so it's not really that big of a deal. It's easier to see if we used a bigger array, or a bigger set, but it takes forever to generate just 50,000 elements and stuff. So, but you can still see the difference here if we use the optimized version, right? So if we change that to optimized, see that it's much different, right? Just for rewriting that one bit. I mean, that's something fairly simple. Like, I mean, it was kind of contrived.
Your first generation, your Gen 0 collections, it's entirely.
Right. Because it's not, it's not creating any. I mean, it's creating the resize array or whatever. But I mean, really, that's just an array, more or less. So, I mean, you're not getting any, garbage collections, which, depending on what you do, like this. I don't know if anyone here reads like the Stack Overflow dev blog and stuff, where they've done like really crazy optimizing stuff with .NET. But I mean, that's the kind of situation where having no garbage collections is a big deal for them, right? Because the garbage collections on their server, I mean, they've written blog posts about, like, we had to optimize this code because, every so often the garbage collection would kick in and just kill the server because it would be too, like, the garbage collection would stop, it would start garbage collecting stuff, and then it would go crazy because it had tons of, dangling pointers and references and things. And then, I guess all the requests that built up in the meantime on the server, it would just crash the server. So it turned out to be kind of a big deal, and even just the performance alone, you can see here that for such a small example, it's what, 5-ish times faster, right? So, and that's going to scale as the collection gets bigger. So if it was 100,000 elements, that might be more than 10 times, right? So again, just a simple example, but it is kind of a big deal in some cases if you really need the performance to use the right data structure and optimize the function. So I mean, it's one thing, fine, go ahead and write the stuff with pipeline operators and all this, and it'll be easy to write the first time and get it right. But if you need the performance, go back later on and fix it to be optimized, I guess.
Question?
Sure.
So, from a readability perspective, I think I would say that the first method was more readable
Oh yeah, for sure.
than the second method. And there's always a trade-off that when you start optimizing things, you lose readability. And you know, in traditional languages, you're always kind of directed to write something that's readable first and then optimize when necessary.
Right.
Would you recommend the same tactic?
Oh, I mean, absolutely. Like I said, I would almost certainly write it the first way myself the first time, and it's really just, it may be fine. If it's something really small, or let's say that we're only, like in that case, I had 50,000 items in the set, right? So let's say I had 10 items in the set. Well, that's not a big deal at that point. I mean, it's going to be such a trivial difference that it doesn't, it's never going to matter basically. But I'll talk about some stuff in just a bit with design, but it's really important. If you think, let's say that function might eventually take 50,000 elements or 1 million elements or something, then you may want to go back and just preventatively rewrite it, just to make sure that somehow it doesn't crash down the road or whatever. But I found that if you rewrite it, so like the second one there, you can even do some more optimization of that one, right? And shave off another like 5% of the script or something. But that one is even so ridiculous to read that you would just never want to read it again. It would just be like, let's just write it and we'll play with some logical and leave it, right? So, but you can get, like I said, with the 80-20 rule, you can get most of the optimization. It's still fairly readable if you use comments. Like I liberally use comments in our code. I mean, if you just did a naive count of our code base, I'd probably say that 1/3 of the lines in there are comments. Because again, since I'm the only coder, I have to remember everything that I've written. And our code base is now on the 30,000 lines or something, right? So if you can, as long as you know what the thing is supposed to do, and it's well commented and you use good variable names and things like that, I don't think the readability suffers too badly. So, all right. So moving on. So scalability. It's not just a buzzword, right? So it's not one of those things that people just talk about and sell themselves, hardware and software and all that stuff because scalability. But it is important that you take that into consideration during the design phase of an application, right? So, it's very rarely something that you can just tack on later and say like, all right, we've got this application now, let's make it scalable. It just doesn't work that way.
Yeah, didn't you say you had your application done in C# in the beginning, and you migrated towards F# and you wanted 30,000 lines, you moved to 6,000 lines. You just said you're up to 30,000 lines.
Yeah.
Now.
Yeah. So I mean, we've added a huge amount of functionality since then. So we've added all kinds of extra compiler stuff under the hood and just various analysis, and we do a bunch of integration with Visual Studio now that we didn't do before. So it's like really awesome COM stuff and F#. Like, I mean, you can. The cool thing about F#, it doesn't do some of the fancy new C# stuff with COM, but you can, kind of like write your own little functions here and there to handle some of the COM junk. But it's not nice, right?
How does it play with SharePoint?
I don't know. I haven't tried it, but I mean, I really haven't run into anything. In fact, let's say I've run into one thing specifically to date. And I've been doing this for about a year. I only write F# now, basically, right? I only run into one thing to date where F# just didn't work right. And it wasn't really F#'s fault. It was that thing's fault, and that was nhibernate. So I use nhibernate for our website, like to do some things in the back end of our website, and it does some stuff with like C# auto properties and all this other junk that C# just does by itself, and it assumes that will be the case.
I mean, that's really the issue. It makes tacit assumptions based on compiler details of the current C#
compiler.
Right. So I mean, so essentially it's assuming that you're using C#, right? Instead of saying, let's do this in a language independent way, which, I don't know, maybe they'll do that at some point. I think they're going towards that, but that's the only thing I've ever come up with that I just said, well, this won't work. Now, on the other hand, since F# is a newer-ish language, in terms of being, a bigger community, you will find things that there may not be like a project template for something, right? And you just got to kind of grab it, junk out of the C# template and build it yourself, right? So like if you get the Visual Studio integration SDK, right, which is what we use, right? It comes with all kinds of project templates and examples and everything for C++. If you just do native C++, and then C# and VB, and it doesn't include any F# examples at all, right? Which, I mean, again, is something that's fairly obscure, so I wouldn't expect it to include that stuff. But it's just one case where you kind of got to roll your own, right? So.
Just go back to the point that you mentioned at the start that you observed a big performance gain when you rewrote everything in F#. How much of that was due to the fact you think that you just rewrote your code versus actually moved to F#?
I mean, that's certainly there. I mean, there's a bunch of stuff in our old code base that really just wasn't that nice. One of the things with F#, its basis is in ML, right? And so ML was designed as a language to build compilers, and so it's sort of using the tool for the job. So even little things like casts, right? So let's say you had an interface for an abstract base class, and you derived some type A, B, and C from that thing. Maybe in F# it's better represented as a union type, right? So under the hood, union type is tagged, right? It actually uses like an enumeration value, like 1, 2, 3 for those cases. So when you compare, it's like in pattern matching. If you look at that in Reflector in EIL, you'll see that if you're doing some not nested pattern matching, but you're just like, is it this case, this case, this case? It just matches the tags, so it's a really fast integer comparison, right? Whereas in C#, maybe you just have to cast it or use the is, like C# is this, right, or as this. And in EIL, that'll use like the is instruction, and that's going to have to go in and check stuff in the .NET compiler, in the runtime, typing and all this, right? So it's got to do like dictionary lookups and all that inside the framework. So it's faster just because it does that integer comparison, which is really a better way to do it, right? So it's little things like that again, when you multiply it by a huge code base, can add up to little things, right? So.
Is there a converter from C# to F#?
No, not that I know of, unfortunately. I mean, one of the things that I really liked about F# was that I had never really done any, I hadn't done any programming language research or anything like that. Because I'm not, I didn't come from a CS background, I came from a math background, right? And I had done C# for a long time. I'd gotten, let's say, good enough in C# that if you could do it with C#, I could probably do it, right? But to switch to F#, I didn't know anything about functional languages or whatever. And it's fairly straightforward to start porting stuff over. I mean, you don't have to go crazy, and the first time I port this over, I'm going to make it super functional to use every feature F# has to offer, right? I mean, you can get a fairly nice port and just get stuff working in F#, and then later on go back and kind of say, oh, well, I'll fix this up to use more functional style, or I'll change this thing to be a fold or something like that, like over a set or array, and then that'll ensure some computation is going to be correct when it spits out, right? So that was one of the big things, is that it was easy for us to port our code over, and then whatever was not quite right, we could just fix it up later, and then or make it more functional or something. And it's a fairly shallow learning curve, I would say. But you have to spend some time learning it. So, I mean, would say it's much easier than something like Haskell, which, I mean, if that's your first functional language, it's not terrible, but it's not super easy either. Question?
You mentioned Hibernate. How would you do ORM in a Sharp?
Well, I mean, now there's the type provider stuff, right? So it's not out officially yet, but so that would be one thing is if you had like an ORM type provider thing, you could have nhibernate type provider, and nhibernate generates the proxy types in fly with reflection or whatever in the hood, whereas the fsharp type provider could just look at your database schema and just generate all the types right then and there, so that it doesn't maybe you don't have reflection permission on your web server, so you can't run reflection in medium trust stuff. So if you run a web server like you're supposed to run a web server, it's going to run in medium trust, which means you don't get reflection. And so that's one big advantage right there is that, because it's all statically compiled, you don't have to worry about that. And if you have anyone that's used nhibernate, will tell you that if you've got a huge nhibernate project and the first time you hit the site, right, to start it up and warm it up in ASP.NET, it takes forever because it's got to traverse all kind of stuff with reflection and generate types and validate your database schema and whatever, and it takes forever just to do that, and it's every single time you start the site. So, but I mean, as of right now, if you had to do it, I don't know, Rick, maybe. I mean, is there anything better?
There's functional in Hibernate, which Robert Pickering made, but I don't know how well it's been maintained.
There's also a Soma,
Oh yeah, Selma, yeah.
which is actually a fairly, I mean, it's not at the level of sophistication of some other ORMs, but I would say it's definitely in the ORM space that's very F-sharp centric. It's certainly a little bit closer to ADO.NET than Hibernate is. It's not trying to, it doesn't do a lot of, it attempts to abstract away and hide a lot of the boilerplate, but doesn't go so far as to give you a whole new embedded DSL to learn for how one creates queries and such. So there's trade-offs. So
Yeah, no, I hadn't heard that one. I mean, I've seen that functional in Hibernate, but I think they did something with like quotations and link, and I think it's more like a proof of concept than something you want to really. Question?
I missed the first half, but your company, you write stuff that takes IL and it lets it run on the GPU.
Yep. So
are you guys taking advantage of like expression trees, like in F# or even the C# version?
no, we don't do well.
Do you have
So
plans
right now
to?
we have our own implementation of stuff.
Sure.
I don't piggyback on that. Number one, because when we, I don't know if we'll stick with this, but when we originally built GP.NET, I didn't want to be stuck on .NET 4 essentially. Because I figured there would be a lot of people that would have legacy code, and one of the neat things about doing things the way that we've done it and saying, well, we don't want to do native code and tie it in somehow, and is that we can have people say, okay, let's just take part of this application, and it doesn't have to know that, all right, well, I need to do a matrix multiply here or something. Well, it's just, instead of doing that on the CPU, well, I'm just going to take that and put it on the GPU now, right? But the rest of your application doesn't need to know. And when you call the matrix multiply function, it does its thing, and then it spits the answer back. How it happened, it doesn't really matter, right? I mean, the whole thing with functional languages and all that kind of stuff too, right? So yeah, I mean, we don't do anything with that yet, but I was going to mention some stuff later about things we're adding to GP.NET, and that's actually going to be one of them. Is there's a nice library that NVIDIA has built for CUDA right now called Thrust. So they built this library called Thrust, which is essentially some sort of like functional type stuff for the GPU, but it's written in C# using templates. So, we want to build something like that, but we'll probably use like expression trees, right? So we want to. All right, so let's keep going. So I want to talk just briefly about scalability, right? So like I said, it's something that really needs to be considered during the design of your application. You can't tack it on later. And so, I've found that the best way to do this is to scale your application down, not scale it up, right? So assume that your application is going to have to run on a really big, for us would be stuff like, several GPUs, or it's going to have to run, at the absolute lowest latency or something, right? Or, if you write cluster-enabled apps, assume it's going to run on a big cluster, not a cluster of 5 nodes, right? Assume it's going to be a cluster of 1,000 nodes or something. And the thing with that is that it's more work up front, but that work is absolutely amortized over the lifetime of your application, because you won't have scaling issues later. You won't find random, like, oh man, I didn't realize that latency would be a problem with this, and then you go to put it in the cloud, and now your database cloud server is in a different thing than your web cloud server, different data center, right? And now latency is an issue because that's the case. I mean, I wrote something. I think the first time I actually used nhibernate, right? So back to that. I wrote something and I tested on. I had an actual web server that I had gotten at my house and I used for testing and things. Built this web app. Nhibernate, man, it saved me so much time, and went to go deploy it, and I deployed it, and the application was just ridiculously slow, and it took me a while to figure it out. There wasn't all nice profiling tools and stuff for it then. So it turned out that I had made one stupid database query, basically, and it was just hitting the database repeatedly, and because of the latency then with our database and the application and all that stuff, it just killed the application, right? So something that if I had tested it like that up front and assumed they would be separate, I would have known that right away. So, and again, it does cost more up front, but because it is going to keep you from having random issues like that, it reduces your overall cost risk, right? So that's another big thing too when you're trying to figure out, what is this application going to cost us to build? It's going to, we're projecting costs for maintaining it and building it and adding features and stuff for 10 years, when you try to build a big software app, right? So if you don't know that there's these problems and you just figure you'll solve them along the way, you don't know how hard they'll be to solve along the way, right? It can just be like, oh man, we gotta rewrite the whole app. Right? So if you do it right the first time, it's less risky. So just a brief example, I was going to say something about, if anyone here has heard about auto sharding, database type stuff, right? So if you have a huge database backed web app and you want to you're going to be dumping huge amounts of data in it over some period of time, and but it's going to be a lot of data, right? It's not going to be like 5 terabytes of data or something where you put that on a SAN or a RAID or something in one server. You want Facebook style, like I'm going to put 100 terabytes of data or a petabyte of data or so forth, right? And you can't put it on one server. Well, if you design your application from the get-go to use like an auto sharding database, then you won't have scaling issues down the road, right? It's just like, okay, well, add for shard, add for shard after that, and so forth. And your application doesn't need to be rewritten to take advantage of that. It just doesn't work, right? You just add a new shard in and replicate stuff, and then it's done. If you're using a legacy, like monolithic type database server, nothing wrong with that. It's still ideal for a lot of apps, but maybe not for that app. And if you write it that way and just assume it'll scale, you're going to hit some point where it doesn't scale anymore, and then it's not like, well, let's add more RAM to the server or something. It's just, let's rewrite our app again. You hit a brick wall and you're stuck. So just a couple of brief points on that. I would say, again, test your apps at a huge, whatever scale is possible for you, right? So I mean, if you can spin up a bunch of cloud instances or something and test your stuff on a big number of nodes, like maybe you're really only going to run your app on a 5-node HPC cluster, but spin up a bunch of cloud nodes, just for like 5 minutes or something, right? And push your app out to it. test it on a bunch of nodes and make sure that there's no issues, where it's like, oh man, I hard-coded this thing to 5 nodes and now it's working. So, and like I said before, this is key. Again, reflector, open stuff up, look at the IL, check it out. There may be some kind of thing you did that the F-sharp compiler couldn't optimize your recursive function into a tail recursive function, right? And if you test with a fairly big data set, right? So let's say you have an expression tree, right? You're traversing this tree. If you do it in a non-tail recursive way, then for 5 node, 5 depth, right, or 10 deep tree or whatever, it's not even a big deal at all, right? But what about like a 15,000 deep tree or something? It's just going to crash, right? It's going to overflow the stack and break your app. And it's really, may not be that hard to fix. I mean, just be like, oh, I got to move this bit of code around and it's fixed.
Have you found, like I haven't really, I use a lot of recursion, and I found a place where I could look at something and tell it could be scale optimized and had it connected to it, even with like recursive functions. Have you run into that?
I've run into a couple of small things, but it was probably just because I was, it could have been something like only ported our app over, where, by then, at that point, I only had a little bit of F-sharp experience, right? I mean, even now, I really don't run into it a lot, but again, I mean, it's one of those things that it's sort of better to be safe than sorry, and even, now that I write tons of F-sharp, and I've written tons of F-sharp, talks, whatever, right? I mean, I still make mistakes sometimes. So you just never know that, you don't want to assume that you're like, man, I wrote that, it's fine. I mean, if you really need to make sure, especially with F-sharp, it tends to be something where you don't need to do a lot of maintenance on your code, I find, right? So it's like if you write it and you get it right, then you just pretty much leave it forever. I mean, it's like, hey, this thing does, I don't know, some cache, whatever, and I can reuse it, and it's good, and I know it's optimized, so.
You stress test your applications. You write a code.
Yeah.
You stress test it.
Yeah, I mean, not all of our code. So some of it tends to be kind of like it tends to be kind of rough to test it really well because there's so many like moving parts to it. Because we do like intercepting methods and just the stuff, but it's not going GPU. Oh yeah, no, I mean, but there's unit testing, right? And then there's like stress testing, like let's just take this function and we'll hit it with every core of the machine, and we'll see if there's any deadlocks or something like that, right? But yeah, I mean, we do stress testing, and we do, I do like integration testing, which would be kind of like let's just test this one function, like right, so I write it, it works, and or I'll run it through some, I'll build a couple of unit tests for it, and test something or something obviously stupid that I did. But let's see. So again, quickly testing the best hardware you have access to. So like I was saying about, hitting with a lot of cores. So if you can afford like an 8-core Xeon or something, like it's just a workstation, right? So it's not something you got to go out and buy like 1,000 of these machines, but if you can spend a little more on your workstation, make sure you have enough RAM to really stress test stuff. If you have an 8-core CPU, or I think AMD has come out like a 16-core CPU or something, right? I mean that's really a good way to say like does this application scale to a lot of cores, right? You may only run it on a dual-core server. It doesn't really matter, but when you've written it and you've tested it, you know that it scales up, and then it's just like okay, well let's get a bigger server, copy thing on it, and I know it works, right? So, and also as a bonus, you should test on the worst hardware you can find. So we, when we're doing like GPU and hardware testing and stuff, generally I use like an NVIDIA Tesla, which is like a dedicated computing GPU. Got like a really fast processor, tons of memory and all that. But I also tested like a really junky, like old, like 3 years ago, bottom of the line card. Just to.
AMD.
Well, we don't support AMD yet, but the way we've put GPU.NET together, it's it's hardware independent. So I've designed it so that we can just have plugins in for different hardware, and like it's all modular, so that we can just kind of say, all right, well, we want to support AMD now. It's just I'm going to implement this stuff, and then there it is. So the only reason we haven't yet is because AMD has been really focused on their OpenCL stuff now. They used to have their own like intermediate language kind of thing, kind of like .NET, right? And that's what we were going to target, and then they did away with that. So I think that they're going to, we've talked with them about finding some way to do some functionality. I don't know what we'll do, but it's there. I mean, we've also talked to some other hardware manufacturers as well. So.
How about mobile? Although Java still there.
Yeah, so that's another really cool thing that we've been talking about building. And so if you write like an FFT or something like that, right, and you want it to run wherever, right? So let's say you want it to run on the GPU, you want it to run on the CPU when there's no GPU, or you want it to run on mobile, optimized, right? Let's write something, like literally, let's write something once and then we'll figure out how to run it somewhere, right? We've again designed GPU.NET with that stuff in mind, so I haven't really done any mobile testing yet, honestly. It hasn't been a big thing where people are like, oh, why does it fortunately I can run on mobile and a ridiculous big GPU, but it's definitely there, and especially now that some of the new stuff like from NVIDIA, they've got quad-core ARM, now with SIMD like acceleration, and I mean, comparatively to a huge GPU, top of the line, like the performance is 20th or like 100th or something. But again, like sometimes it's just relative. So comparing my top of the line Tesla, whatever, to my laptop GPU, right? I mean, the Tesla is like 20 times faster or something. But relatively, to the CPU, I've got a Core i5 mobile something, right? I think that is spec'd at like 15 gigaflops or something. And again, remember that's going to be like max performance. So it's like if you do everything right, you'll get 15 gigaflops. My lower end range mobile GPU does like 180 gigaflops. So if your application can be moved over to the GPU, you'll still get a performance gain even on lower end hardware, right? It's all relative.
I was just wondering, as sort of a side question, do any of the current phone operating systems let you get close to that hardware?
Android does, right? So Android, actually, they've got this thing called Mono Touch now, right? Mono Touch to this, and the thing with Android is that because I guess you have more freedom to do crazy stuff with it. I don't know the details, but there's Mono Touch for iOS, and I think it just you write like C# and then it like extracts Objective-C code out or something, and then you compile out of Xcode. But Mono Touch is actually a full mono VM on Android, and I guess they've optimized some for the hardware and all that. But that actually would let you get full hardware acceleration. And I think the new Windows Phone Mango, whatever, I think that, I don't know if you can get to it from regular C# and you can't do some crazy like something in ARM or assembly. But I know that the XNA implementation on it now does do ARM SIMD, it's called Neon, right, acceleration. So I think that's just been out now. So again, I mean, our main goal is really like, let's not write, there's so much scientific code out there that's really, really tied to the exact like platform and like not even major revision of some specific compiler, but like this exact 10.1.6, like don't compile with anything else of Fortran. And it's stuff like that that it's really a shame because there's so many cool like numerical and scientific type projects out there, and to have them tied to a specific OS and all that stuff is really kind of a shame. because it really limits what you can do with stuff, right?
Mhm.
So I mean, that's probably one of our main goals with GP.NET is to make it where you can write accelerated code in a way that's convenient for you. So I don't know if I have a slide for it later. Yeah, I don't think I put a slide for it later, but one of the things I was going to mention was how we've changed the API for GP.NET. So when I originally designed it, what I figured out was, hey, we can do some analysis and all this, and a lot of stuff we can just like hide it, under like at compile time. I can just go back and jam in a bunch of extra IL into your own code, and then we can just handle all the GPU stuff by ourselves, right? Like, don't have a budget. And it turns out that that's really good for some people, but it's not good for everyone. There's still some people that we meet. Like I went to Seattle a few weeks ago, and I was talking at this supercomputing event, and one of the things was that we were asked by people was people that do the Fortran and the crazy low level like C macros like crazy. They want to be able to just tweak the hardware to like an absolute 100% of what they can get out of it, right? And so those kind of people, they don't like to be told that, hey, just leave it, it's up to them. They want to be able to tweak it. So now we're kind of splitting up the API. So we're doing like a low-level API to expose a bunch of stuff. We'll still have that really basic API that's available if you just it's like check an option and it'll just do it for you. And then on top of that, we're building like stuff with Link and F-sharp. So we'll do like an F-sharp. Just the kind of stuff that you'd be used to using. So like F-sharp has the array module, right? There's like array.reduce, right? And you can just say, okay, it'll take the reduce function that you pass it takes two elements of whatever type is in the array and returns one element, right? So however that happens under the hood, whether it gets split up on TPL and reduced, and then let's say you have a quad core, it's going to split stuff up across cores and then reduce the last results together, right? Or just all on one single core with a for loop, whatever. But we want simple, like sort of accessible things like that to let people write accelerated code that you're going to get near, let's say 90% of maximum performance for doing 20% of the work or something, right? And without having to deal with all the interop. So real quick, I guess. Yeah, 30. Alright, so let me go over some of the stuff now with GPU computing and all that. And if I don't get to some stuff, then I'll put the slides on and I'll come back and do it all the time.
I can definitely have that.
Yeah. So let's see. All right. So parallel computing. So what is the big deal with HPC and GPU, and how does it relate to scalability? So scalability directly related to parallelizability. It's a really long word, sorry. But basically, how well can your application be parallelized? How well can your algorithm be parallelized, right? And there's a law, so like Moore's law, which is not really a law, but sort of a rule or guideline, Amdahl's law, and it's basically said that you can get speed up proportional to log of your processor count. And something I failed to put in there was that it's not just log of your processor count, but also what proportion of your algorithm can be parallelized, right? So if only 10% of your algorithm can be parallelized, well, no matter how many processors you throw at it, well, it's just not going to. You'll get some scaling, but you won't get that much scaling. Where something that is what's called embarrassingly parallel, right? It's like a Monte Carlo sim where it's like, okay, I'm going to generate this huge number of elements, and for every single element, I'm just going to use like a mapping function. Basically array.map or something, right? There's no dependence between elements or anything. It's like 100% parallelizable, right? So that's a really good one. Probably Monte Carlo is the easiest thing that you can accelerate on GPU. And that's the kind of thing that people that run on a Monte Carlo on GPU will invent these like crazy workstations with, as many GPUs as they can jam in there, and like huge fans to keep it all cool. It's like 2,000 watt power power supplies and stuff, right? So I mean, again, the parallelizability is a really big deal because your application can't be scalable if it's not parallelizable. This is a so. All right, so what are the two kinds of scaling? So there's scale up and scale out, right? So scale up would be, let's just take the server we have and we'll add a faster processor, right? And that's pretty simple. So when that's an option, it's easy. Like let's just plug in a processor and it costs $400 easy. But the problem is that it moves at the pace of technology innovation. So you're kind of bound by Moore's law. I mean, if you buy the fastest processor out there, then if you want a faster processor, you have to wait until they invent a new one, right? So, and it can get expensive. If you look at CPU prices and things, for let's say Intel Xeon, the mid-range stuff is about like you'd expect, like a few $100 to maybe like $500 or something, and then it rapidly moves up for just little increases in speed. So I mean, to move from like this is totally arbitrary, but like to move from a 2.8 to a 3.0 can be an extra $400, right? You might as well just get two processors in. But if your application will scale across two processors, then you're stuck, right? You've got to buy the faster one. So then there's scale out, right? So scale out would just be let's put more nodes, so more processors or whatever that is. And the big work here is that you've got to redesign your algorithm to scale out, right? And that's the biggest thing with GPU computing, and I think that's the hardest thing for people to grasp is how you got to redesign algorithms and how algorithms need to be ways, but I don't know, let me come back to that, I'll think about it. It's just basically really hard to move some apps over to GPU just because you have to program in such a different way, right? So it's also pretty cost effective to add new nodes. So like I was saying before about the sharding, right? If you have auto sharding, database, then to scale your app, you're not adding an extra 60 gig of RAM or something into your database server, and it's really expensive. I mean, it's just like you could add a $2,000 commodity something web server, just plug it in, and that's it, basically, right? So really, pretty cost effective. Here's the big one. So not all algorithms scale well. So people, I think some people that I talk to think that GPU computing is like magic or something, right? Like, man, my thing will be 1,000 times faster, and it's not really the case all the time. So everything, like I said, is going to depend on how parallelizable your algorithm is, amongst other things, right? I mean, there's still other considerations to take in. But the big thing is redesigning algorithms. So even now that stuff like CUDA, OpenCL, GPU computing has been around, in a sort of big way for, let's say, 4 years-ish since CUDA came out, right? And even with that, I mean, there's still lots of algorithms papers coming out in terms of, oh man, well, we figured out some new way to do parallel sorting on the GPU, and now it's 10% faster than the best known one before, right? And it's still sort of like a wild west of algorithm research. I mean,
yeah, but doesn't that just go right at the problem with writing algorithms and be a complete problem? I mean, in a sense, you're trying to balance. You're trying to find. It sounds like you're trying to find an algorithm in various cases. Is that theoretical problem?
It's really. I mean, the way that I guess maybe it would be a good way to describe it would be. You need to come up with an algorithm that gives you a better way of just throwing an arbitrary amount of computing power at the problem. So it's something that you could say, like, if I just had, 10,000 nodes, or something like I was saying before, if you assume that your things have to be infinitely scalable, you get into things like, I was going to guess you would just stay here, but I don't know all the time with MPI, MPI. So on, like what we were talking about before with Rick and I, with the forcing the lazy and all that, where it's going to do like a monitor pulse and everything. Well, when you have like atomic functions like that, processor, you're doing what's called shared memory concurrency, right? So whatever threads, processors, whatever you know are considering to be a node, right? They've got to share some memory and communicate that way. And the thing is that it gets kind of hairy quickly, right? And so with use MPI, you use this like message passing stuff, and we just. So let me get back to that in just a second. So quickly, MPI, if you've never heard of it, it's like a standardized interface to pass messages, whatever you want to call a message, right, between nodes. And this is kind of the important part, is it doesn't say what a processing node, or I just made that up, but a node, it doesn't care what a node is, right? And so a node could be any of these things. A node could be like a lightweight, or you might hear green threads, right? So that's the huge draw of Erlang, is green threads, where Erlang, you can design some app that runs like a million threads or something at once. They're not really all running real threads at once. They're kind of using like coroutines and stuff like that, right?
What about Lua?
Don't know. I haven't used it very much. But I mean, there are other like languages and stuff that do lightweight threads. And there's even libraries and things like if you use Retlang, right? For that, we actually use Retlang right now to do like fibers and all that kind of stuff, to just do message passing, right? But it could be user mode threads, kernel mode threads. It could be a core, core or cores on a specific physical processor, right? It could be multiple physical processors in a single machine. It could be accelerator card, like a GPU, like let's send it a message and it sends us back a message. Or it could even be different physical machines, like different nodes in your cluster or something, right? But the point is that you're not specifically defining that, and that's what I was getting back to with shared memory concurrency. Is it's almost like how you use dependency injection to say, like, I'm not going to be stuck using this one class or something, right? You inject a dependency. That's almost kind of like you can think NPI that way, where we're not saying what is in processor node. We're just sort of defining a general, this computation have to pass messages around to take care of this and that, and by doing it that way and not saying they've got to communicate via shared memory. You could implement NPI using shared memory, right? But by being more general about it, it leaves you, some extra freedom to design your app. So back to F#, right? So how does NPI kind of relate to F# here? So you think of async workflow, right? So async workflow, you execute a function, and it really takes like a callback and a closure or whatever, and puts that into the .NET thread pool, right? So it's going to execute something on the .NET thread pool, and then later on, you can say, okay, I'm ready to get the result of that, and then it's like you're going to get a message passed, essentially from whatever thread executed on the .NET thread pool back to the thread that you. So if you think about that, that's pretty much what the async workflow does, just like NPI does, right? Mailbox processor, same thing, right? They've shown that example a bunch, like on that Sharp website. Using async with a mailbox processor and a recursive loop where it just processes, whatever. That's basically what MPI designed applications are going to do, right? It's just going to sit there, whatever nodes, like let's say you have all your nodes in a cluster, they're just going to have some kind of server thing that sits there and listens for messages on TCP, and when it gets a message, it'll process it, perform some part of a computation, and return the result through another message, right? And the big thing here, so this is like, I don't know, maybe I should have pulled it up more or something, but using pure functions and not having like some global state that needs to be synchronized, I don't think that can be understated at all. I mean, sorry, it can't be overstated at all. So it's really, really huge. And so from someone who writes like a lot of compiler stuff now, right? If you go through and read, compiler literature about like F#, Haskell, and all these other different languages, compiler is so much more free to do optimizations of things when you're using pure functions than if you are using some kind of global immutable state, right? Because you just can't, with pure functions you can make certain assumptions like, hey, I know none of this stuff has changed, so I can just do whatever I want with it, right? Whereas, if you see that, like let's say in .NET, you've got a class and then there's some kind of field in the class or whatever, you don't know where if that field value is going to be changed. Like it could be changed in the middle of that method running, right, by another thread or something. So the compiler can't optimize that to certain things, right? So quickly here, I think we're about to run out of time. So I'm sorry, big draw today, GPU computing. I didn't get to it as much, but we'll talk about it here real quick for about 10 minutes. So if you haven't done any GPU computing stuff yet, the big vendors and hardware, NVIDIA, right, is the biggest by far right now. Their main computing line of dedicated compute stuff is Tesla. If you plan to do GPU computing on Windows, that is definitely the one you want to buy for right now, right? So the difference is beyond, I don't know about FPGA and Mike just came out and testing and things like that right now, but so Tesla provides a special driver that lets you get around some graphics issues with Windows 7 and Windows Server, 2008, all that. One of the kind of annoyances about GPU computing is that because it's running on your graphics card, right? If you run some computation on your graphics card that you're using for display, then it can't drive your graphics and do the computation at the same time, right? So the problem there is going to be that your display essentially freezes. So like I was saying before about milliseconds, microseconds, so we optimize things. It's fairly unnoticeable if you freeze a display for 100 microseconds or something like that, right? I mean, no one's going to notice, or maybe even 50 milliseconds-ish. But if it freezes for half a second or a second, I mean, it gets weird with the mouse jumping around. And eventually, what happens is, I guess in the old XP days, there was a lot of issues with graphics drivers and things. So for Windows, I think it was Windows Vista that they started it, but it really became robust in Windows 7. Is they did a new driver model for graphics, and basically, if the graphics card hangs for more than 2 seconds, let's say it hangs could even be a computation, it'll kill, it'll basically reboot the graphics card in a sense, right? So your computation dies, stuff goes crazy with the graphics.
Blue screen? You get a blue screen?
No, so that's the thing. So that's what they wanted to prevent, right? So that was the whole thing. Like in XP, that would just crash the computer, or I don't know, erase all your files or Windows, right? But now in Windows 7, that's why they built that, the graphics driver that way. And unfortunately, I don't think they really built that with GPU computing stuff in mind, because there's really not a good way around it. But what NVIDIA's done, I mean, if you use Linux, you can just not use the X server and just run everything from the console. If you're using Linux, you're probably doing that anyway. But the Tesla comes with a special driver, basically, that will let you run it as just a compute card and not graphics or anything like that. You can run headless, right, for a server or whatever else. So, and AMD's got some sort of compute dedicated cards. I don't think they have any special driver stuff. I think they're more Linux oriented. And Intel's just come out with their mic board. I don't think it's not out for sale yet. They just put it into testing and final revisions and things. That looks pretty promising too. Then there's FPGA type stuff. Not really GPU, but it gets mentioned a lot with say the audience. So I'm just gonna go through this. So this is different APIs and stuff you can use. The important thing to note is that they're all pretty much C++ and Fortran based. I don't know of another compiler that, there's lots of wrappers like for Python and Java and everything else, but pretty much everything else under the hood will generate like CUDA-C or OpenCL-C or something like that, and put it through the driver or the the compiler, generate the actual device code stuff it needs, then pull it in, then call it. So it's not really compiling Python bytecode to device GPU device code. It's not really compiling the Java code to device code. And so, I mean, I think we're the only one that actually just like we're not using your compiler. We'll just build our own. So, like I said, I mean, it was something that when we started out, I figured like, hey, we could probably just do like a quick interpreter or something and be done in like 6 months, but not really the case. So now we've got full compiler, for .NET and GPU and all that. So I guess the one thing that people want to hear is that there are huge performance gains to be had, and that's true. So like I said, it really depends on your specific application. So I would say a good rule of thumb would be is if it's a very data intensive app, right, you should get pretty good performance gain. With the caveat that you've got to be able to move your data to the device and then just leave it there, do your computation, and then just be done with it, right? And the more, the super important bottleneck in GPU computing is transferring data between the host and the device. So, not just because the bandwidth is limited, but because there's also, no matter what you do, there's a latency associated. Like, even if you, didn't use an OS, wrote your stuff in raw assembly and whatever, PCI Express, there's like PCI Express host controller latency and stuff that, your application will just not scale past that at some point, right? So, but I would say it's pretty reasonable that if you just took a generic something that processed data, you could throw it on a decent card and get something like 5 to 10x out of it, right? And so that's pretty cool because it's not like 5 or 10%, it's 5 or 10 times faster. And there's been plenty of things where people are doing really like a Monte Carlo type stuff where you can just throw as much hardware as you want to buy at it and it'll scale. So if that's the case, it's like, well, I get 1,000 times performance, and if you're doing some kind of simulation that takes 24 hours to run, right? That's what 86,400 minutes. If you run it 100 times faster, right? Well, let's say you run it 1,000 times faster. Well, instead of 24 hours, it's an hour and a half now, right? So, or sorry, 86,400 seconds, so it'd be a minute and a half, right? So yeah, so I mean, huge performance gains to be had potentially, but you can't just assume that. Again, it's all about parallelizability. So if you try to parallelize something on GPU, disclaimer, it may not really work. Depends on your algorithms. And one thing that naysayers or whatever are always quick to point out is that double precision is slower on the GPU, slower than single precision, right? So it's just because of the way the hardware works. So let's say you get 1,000 times speed up out of, at single precision levels, we only might get 500 times speed up at double precision.
That's still faster than do a double precision, not on the GPU.
Right, exactly. So I mean, it's all relative. Again, I mean, it's not something you can just say, well, that application, I looked at the code and it's must run faster. I mean, you've got to know what it is, right? You got to know the algorithm and all that. But
how much it matters too is like it's all between 0 and 1 or something. Like how would be? Doesn't make a precision matter for most of it.
And another thing too, coming from numerical analysis background, there's a lot of ways you can cheat, basically.
Oh, yeah.
Where you can, if instead of saying, I really need double precision, what you're really saying is I need good accuracy, right? Or I need good numerical stability. So there's little tips and tricks that you can do to make sure your stuff is still precise. Like mixed precision is a simple one, right? So you can run part of the computation in single precision, get it close. Let's say for like an iterative solver, get it close, then switch to double precision, do the rest, and it's like, well, you're only spending 10% of the time or 5% of the time in double precision. So the fact that it's running half the speed or a quarter of the speed or something is not going to matter, right? So just some quick resources. Like I said, check out the F-sharp compiler and library sources, for when you're optimizing, real low-level stuff like I showed before. .NET Reflector, is a pretty invaluable tool. I think it's like $30 or something now, $35, but definitely worth it. I mean, it'll save you $35 the first day you have it probably. So, you know, and again, performance profiler, whichever one you choose, invaluable. Or you know, if you really, you know, I need maximum performance, you know, or in the .NET spec, you know, you'll find little things when you look at the IL with Reflector that you can say, hey, well, maybe I'll just tweak this function and now it'll be, you know, 5% faster or something, and it could be big, right? So
One point I just want to make for the group, for anyone who's not experienced this before, the IL thing is invaluable because there are a lot of constructs that can't get translated by Reflector by other tools into anything other than IL. They can't translate them up to C# or VB.NET or even F#.
right.
So knowing the IL is really
Right, so
valuable.
what you'll see with Reflector is that the general idea is, yes, you can look at the IL, but it's made to be a decompiler. So you can like look at it, you know, some application that's compiled like a DLL and see what the source looks like in C, or I mean C#, right? I mean, it won't be perfect like the original perfect source, but it'll be reasonable, right? But there's, you know, C# is not equal to .NET. Like there's stuff you can do in .NET IL. In fact, some stuff that we do like really low level under the hood that you just can't do it in C#. It's just not in the language, right? So I always prefer looking at the IL. So C# doesn't have tail call, right? So I mean that's a big thing for F#. There's no tail calls in C#. So if you try to look at that in the C# Reflector thing, it'll give you an error or just say like it can't decompile or something. So learning the actual IL and understanding what it does is really valuable. So I think that's about it, right? So if you have any questions, you guys are, please email me. I'm happy to answer any questions on stuff we covered or didn't cover.
What's the sort of licensing around GPU?
So we just do per developer license. I mean, I try to keep it simple because it's just two of us. And, I mean, if we were going to do
But
it's a bit crazy like
royalties. It's not a registered runtime license.
Yeah. So we do well. There's no royalties, right? So there's not runtime royalty distribution stuff where like you have to charge your users and then pass it on like a nickel every time they run. Like we don't do any stuff like that. I mean, pretty simply because I didn't want to have to deal with it, right? I mean, I'd rather do my actual job and then do stuff like this than chase people for that. So. So, any other questions?
What kind of stuff are your clients doing with GPU today, if you know?
Sorry?
So what kind of applications are your clients doing?
Oh, so, I mean, right now, I mean, and actually the reason I'm back here in New York is because it's mostly financial at the moment. We also are starting to see some, I mean, we've seen a pretty good amount of academic use, and with the new API stuff that I'm exposing soon, you'll be able to do more graphics type stuff with it. So, when I hit all that stuff under the API in the beginning, you couldn't get to some of the really crazy low-level graphic stuff in the graphics card, like texture fetching, whatever, right? Which for a lot of applications isn't important, but it's important for like data processing stuff, right? So now that we'll expose that, we've already got some people testing and using everything. So.
You're going to support like Mathematica or MATLAB in the future?
Well, I don't know because they already do CUDA and stuff like that, right? So Mathematica has CUDA, like support built in now. I don't know exactly how they've done it. I mean, they may have done the same thing, like I was saying, where they just take like a mathematical expression and like dump out CUDA C and file it to CUDA C compiler and run it, right? But I don't know if there'd be really a reason to do that. I mean, because we'd be kind of like competing their own product, their own product. Like I don't want to try to compete with Mathematica inside their own thing, just because I don't know if it's cost effective. But I mean, you could, if you wanted to take like a MATLAB algorithm, and it should work fairly well to something like F#. So I mean, if you really wanted to.
Is the compiler, is it significantly more aggressive on like F# code stuff that it can prove is immutable? It can analyze statically more? Is it like significantly more aggressive, optimized than that, or?
It kind of is. I mean, it's not hugely aggressive, but one of the issues that you have with GPU computing, and I wanted to get more stuff like this, but I don't know, come back and talk about it, is that there's a sort of unique challenge with GPU computing in that you're extremely resource constrained about where you're running. So you have very little memory to work with. So there's sort of like an L2 cache or something, right? But for the entire chip, which may be running, let's say, like 1,000 threads or something at any one time, you have about 64K. In the new cards, you have 64K of L2 cache to work with, right? Which is really what you want to work with. In the older cards, you have 16K for 1,000 threads, right? So just a little bit of space per thread. You know, on average, you'll probably have something like, let's say 20 or 30 or something like that registers to work with, like 32-bit registers, right? That can just hold whatever value you want. You know, and then you'll have, you know, anywhere between, let's say, like half a gig and I think the brand newest top-of-line NVIDIA cards have 6 gigs of graphics RAM. But I mean, besides them, I mean, the next cards down are like 2-3 gigs, right? So you can't, you know, it's the kind of thing you can't add more RAM to the graphics card like you could just say, like, I'll get a new server with more RAM, but you can't do that. So you've got to fix your problem inside that data size. So it is kind of a big deal with like optimizing the register use and stuff with immutability and all that. So yeah, we do pretty standard. You know, I mean, it's still aggressive, but basically, if you can tell the variable's assigned and never used again. You know, once it's not, you know, you can tell, hey, this is never used again, and you can just you reuse the register basically, right?
So it's dealing with like SLI is not good, even though you can kind of like, I don't know much about it.
So
you put the cards together with like extra keys.
Yeah, so actually, I mean, that gets brought up a lot in like on the NVIDIA forums and stuff. And the SLI like connector, I think they just do some kind of really basic like synchronization thing across it. So the bandwidth is like it's just not doesn't happen, right? So I mean, but some of the things are like they have 2, you know, like physical GPUs and, you know, and their own memory and all that stuff on like one board. So you know, it used to be that even if they wanted to talk to each other, they still had to go back out to the PCI Express host controller. That was kind of messy. But the new NVIDIA cards have 2 DMA engines on the chip, so it can be like computing one thing and transferring other stuff. So you can overlap transfers and you know, and computations. So that is like a way to optimize if you have like 2 host side threads using the same device, right? You sort of like line up a computation, like transfer stuff over while one's going, and then as like the data is transferring back from the first thing, if you start computing the second thing, right? So that's one way to do it. I mean, they also have now like what they call GPU Direct, so like the GPUs actually can talk to each other without going through the host. Like they don't have to, you know, talk to the CPU and then have that intermediate. Like they can just go right over the.
That's the latency they can have.
Right. So I mean, that's like the big thing now is, you know, how we can scale across multiple GPUs. So that's one of the big reasons I want to support stuff like the functional, you know, like you know, modules and things for F-sharp and then Link and all that. Is that not only does it make it pretty easy to build, you know, computations and stuff pretty quickly, it also makes it much easier to scale across multiple devices, right? So if you're saying like, I've got this big chunk of data, let's reduce, you know, like reduce go. You know, I mean, it doesn't matter if it's, you know, 2 CPU cores or 2 GPUs or whatever, right? I mean, it's sort of abstract, so behind the scenes I can say, look, this guy's got 2 GPUs, you know, let's split this up and, you know, I can manage the stuff.
You just think about it like more cores on the same GPU.
Right, exactly. So I mean, you know, it's one of those things like the synchronization becomes key, you know, because there's so many threads. Like you can't say, you know, if you got like maybe 4 threads running on CPU, then you can say, well, each thread is allowed to talk to each other in some way, right? But when it comes, you know, 1,000 cores on a you know, GPU and there's a really small amount of memory that you have to work with, like it becomes, yeah, it kind of it goes back to like the old like C days, you know, when people had like a 286 and stuff, where they did like insane, you know, memory hacks and stuff to get stuff working.
That's where the schools moved to now.
Yeah, basically, I mean, those guys found new employment in that field. So.